Okay guys, so next we want to discuss the factors which depends on conductivity. We know what is conductivity and we are familiar with the three types of conductivity. One is simply conductivity, specific conductance. The second one is molar conductance and the third one is equivalent conductance. Okay, so let me discuss what are the factors that depends on conductivity. Number one, interionic attraction. You know what is interionic attraction? It is the attraction between two oppositely charged ions in an electrolyte, right? Yeah. So that interionic attraction is one of the factor that depends what? Conductivity. Okay. If interionic attraction decreases, which means that ions get more, or ions will be more mobile. Ions have greater freedom to move, which means its conductivity increases. Okay. So the first factor, that is interionic attraction. Interionic attraction. Ready? Fine. Listen. Interionic attraction, that is inversely proportional to conductivity. Your interionic attraction is inversely proportional to conductivity. And the reason is that as interionic attraction decreases, the downward arrow represents decreases. Okay, as interionic attraction decreases, what happens means ions become free. Ions become free. Okay, so greater velocity of ion. So ions become more mobile. Its velocity may increase. Okay, that is the reason. That's why conductivity increases. Ready? Fine. Moving to the second one, polarity of solvent. We know that electrolytes are simply ionic compounds, right? They all can polarize, or they all are in a polar form, right? So if our solvent where your electrolyte is immersed is a polar one, then what happens? The solvent may polarize the ions, so which means ions get more and more what? Ionization. So ionization may increases, its conductivity increases. Okay, we know that our ionic compounds are electrolyte usually, right? Yeah, and ionic compounds are polar. Agreed? Yes. If that ionic compound which is dissolved in a more polar solvent, what happens means the ionization of that particular electrolyte increases. If the ionization increases means more and more ions are produced. If more and more ions are produced means it can cause conductivity. Fine. So conductivity increases. Ready? So your polarity that is directly proportional to conductivity. Okay, directly proportional to conductivity. And the necessary explanation is that if solvent more polar, okay, maximum electrolyte ionized, the ionization of electrolyte will be maximum. Okay, if the ionization of electrolyte is maximum, what happens? Conductivity increases. Okay, more ions will be more electrolyte ionized means its conductivity increases. Next, viscosity. Okay, the next factor is viscosity of solvent or the medium. Ready? The solvent is more viscous. What happens? Your ionic mobility, the tendency to move your ions may decreases, which decreases the conductivity. Okay, so viscosity inversely proportional to conductivity. As viscosity increases, conductivity decreases, because the explanation is that if solvent more viscous, then ionic velocity or ionic mobility decreases. And we know that if ionic mobility decreases, conductivity decreases. Ready? Fine. And the next term, that is temperature. What it is? Temperature. As temperature increases. Oh, what is the relation between temperature and conductivity? We already discussed it, right? Yeah. Temperature is directly proportional to conductivity. Okay. Because as temperature increases, kinetic energy of ions, which means its mobility, that increases. We know that temperature is a function of your kinetic energy, right? Yeah. So as temperature increases, its kinetic energy decreases. Sorry, increases. So the kinetic energy of ions increases, which means that ions are more mobile, or ions have greater freedom to move, which means its conductivity increases. And the last one is somewhat important. That is concentration. What it is? Concentration. So listen the fact. Listen that. Concentration which is directly proportional to kappa. As concentration increases, specific conductance increases. And we know that always your concentration that will be inversely proportional to dilution, right? Yeah. So this is important. What? If concentration of a solution increases, specific conductance increases. Or simply, if dilution of solution increases, which means concentration decreases, specific conductance also decreases. And the necessary explanation is that we know that specific conductance means it is not a bulk conductivity. It is a conductivity or conductance of a specific region. Agreed? Yeah. So this is the specific conductance, right? If we have a cube of unit volume where your electrolytes are enclosed, then what happens? If solution more concentrated, listen, if solution is more concentrated, then what happens? If your solution is more concentrated, then if the solution is more concentrated means the solution have a lot of positive negative ions, right? If the entire portion have a lot of positive negative ions, then our unit centimeter cube also have a lot of ions. Agreed? What do you mean by specific conductance? It is the conductance of a unit volume, right? If the whole portion have a lot of ions, then our unit volume also have a lot of ions. So number of charge carriers increases in a particular volume, in a unit volume, in a specific volume, if the concentration increases. Ready? So if the concentration increases, number of charge carriers or ions in a particular volume, in a unit volume increases. If number of ions in a unit volume increases means no doubt its conductance increases. Specific conductance increases. So if a solution is more concentrated, then number of ions is our charge carriers, we already discussed it, right? Then number of ions in a unit volume increases. Number of ions in a unit volume increases. We know that specific conductance is the conductivity in a unit volume, right? Yeah. So number of ions in a unit volume increases means its conductance increases. That's why as we increase the concentration, the number of ions in a unit volume increases, which means specific conductance increases. Or if we decrease the concentration, or if we increase the dilution, what happens? The entire portion have lesser number of ions, where solvent will be greater, right? Yeah. Electrolyte will be a lesser amount, whereas solvent will be greater one. So in a bulk portion, compared to a bulk portion, number of ions decreases automatically. In the unit volume also, number of ions will decrease, right? Yeah. So conductivity decreases. So as we increase the dilution, number of ions, the whole number of ions decreases, which means the number of ions in a unit volume also decreases. So conductivity decreases. Listen, but our dilution, which is inversely proportional to concentration, that we know, as dilution increases, concentration decreases, but it is directly proportional to lambda m or lambda e. This is important. If we increase the dilution, what happens? If we increase the dilution, then lambda m or lambda e increases. Molar conductivity or equivalent conductivity increases. But if we increase the dilution, specific conductance decreases. Specific conductance means conductance of a small region. But molar conductance or equivalent conductance means the conductance offered by 1 mole of ion or 1 equivalent of ion, which in a bulk portion, right? Yeah. So listen. So what is the reason for this? That we have to discuss. Let me erase this one, okay? Because I need some more space. Listen here carefully. Are you familiar with the Ostwald dilution law? Ostwald dilution law. Do you know Ostwald dilution law? Ostwald dilution law. Ostwald dilution law states that degree of ionization, which will be the square root of constant ionization constant divided by concentration. Degree of ionization will be the, listen, this is kappa specific conductance, but this is the ionization constant that we are also already discussed, or we are usually discussed in your equilibrium. Okay, this is ionization constant. Ionization constant. Okay, so if what is this one? Degree of ionization. I think you are familiar with this degree of ionization. So degree of ionization and concentrations are inversely related. Okay, so the Ostwald dilution law states that as concentration of solution decreases, degree of ionization increases. As concentration of solution decreases, then degree of ionization increases. Okay, that is the Ostwald dilution law. As concentration of solution increases, degree of ionization increases. Listen here. So let me explain this one. This you have to know, because this is a knowledge-based one, Ostwald dilution law. Ostwald dilution law states that as concentration increases, degree of ionization decreases, or concentration decreases, degree of ionization increases. Okay, concentration increases means dilution decreases, you know. So as dilution increases, what happened? Which in turn means that concentration decreases, right? So as concentration of solution decreases or dilution increases, both are same sense, right? Yeah. So as dilution increases, more and more ions get free. That is degree of ionization. What do you mean by degree of ionization? What do you mean by degree of ionization? Degree of ionization is number of species ionized divided by total number of species. Number of species ionized divided by total number of species. If degree of ionization increases, means number of species ionized will be increased, because the total remains a constant always, right? Yeah. So as degree of ionization increases, means number of species ionized increases. That is the meaning. Okay, fine. So as dilution increases, according to Ostwald dilution law, what happens? Degree of ionization increases. If degree of ionization increases, means more electrolyte ionized, and number of ions increases. If more electrolyte gets ionized, means number of ions increases. Okay, hence your lambda m or lambda e increases. Ready? Fine. Or else we can define in this fashion. Lambda m have an equation. Lambda m is equal to kappa into Vm. Lambda m equal to kappa into Vm, or lambda m equal to lambda e equal to kappa times Veq or Ve. This is also equation for your molar conductance. So, and when you are substituting for Vm, we obtain the equation as 1000 into the expression of Vm will be 1000 divided by molarity, and expression of V will be 1000 divided by normality. Okay, that's how we obtain the equation lambda m equal to 1000 kappa divided by 1000 specific conductance divided by molarity. Okay, so Vm means volume of electrolyte contain 1 mole volume of electrolyte contain 1 mole electrolyte. Volume of the system which contains 1 mole electrolyte. Like here, Ve means volume of electrolyte which contain one equivalent electrolyte. So there are two different types of explanations for how the dilution is directly proportional to lambda m. The first explanation is based on Oswald dilution law, that is, as dilution increases, degree of ionization increases, based on Oswald dilution law, right? Yeah. If degree of ionization increases, means more and more species get ionized, which means conductivity increases. And that is one kind of explanation. Explanation number 1. And the explanation which is given in your textbook, that is, as we know that lambda m equal to k into Vm and lambda e equal to k into V. Okay. So what happens? For solution, dilution increases. Vm or Ve increased, right? Yeah. What do you mean by Vm or Ve? It is the volume where 1 mole electrolyte enclosed. Okay, as we increase the dilution, the volume of 1 mole electrolyte will be increased. So volume increased to a greater extent. Okay, moreover, so as we increase the dilution, Vm or Ve increases. Fine. Moreover, if we increase the dilution, it is clear that if we increase the dilution, kappa decreases. Fine. Kappa decreases. So this quantity increases and this quantity decreases. But the increment of Vm is very greater than decrement of your kappa. That's why always which dominate. This decrease to a lesser extent, but this increase to a greater extent. Ready? So, therefore, lambda m or lambda e increases, because as we increase the dilution, Vm shoot up, or Vm increased in a greater extent, but kappa decreased in a smaller extent. So the net result will be an increment of this product, which means your lambda m increases. So these are the two different types of explanation for the connection of dilution with the lambda m e or lambda e. Okay. So first of all, you have to know that as we increase the dilution, specific conductance decreases. Why? Means number of ions in a specific volume decreases. But as we increase the dilution, molar conductance and equivalent conductance increases. Why? Means as we increase the dilution, according to Oswald dilution law, degree of ionization of electrolyte increased. So more and more ions get ionized, which increases the conductivity or the bulk conductivity, molar conductivity. Or from the relation itself, as we increase the volume, Vm or V, where volume of volume of 1 mole electrolyte or 1 equivalent electrolyte, that will increase into a greater extent, into a high value. But the relative decrement or the relative decrease of kappa will be negligible. So the net result will be an increase of lambda m or lambda e. Okay, so anyway, as dilution increased, lambda m increased. So the proportionality of dilution and lambda m is direct, but the proportionality of dilution and kappa will be inverse. So these all are the factors which depends on your what? Conductivity. Okay, these all are the factors which depends on the conductivity. So moving to the next logic, some graphical representation. Graphical representation for your electrolyte. So let me discuss the variation of molar conductivity only. Okay, so from here onwards we are discussing the variation of molar conductivity. Ready? For that, where the molar conductivity of an electrolyte means strong and weak. Okay, so let me discuss the variation of molar conductivity of strong and weak electrolyte. Ready? The idea that is graphical variation. Graphical variation. Okay, so graphical variation means, let me plot square root of concentration versus molar conductivity for a strong electrolyte and a weak electrolyte. Okay, so there is a graph where y-axis have square root of concentration and x-axis have molar conductance. Ready? Then for a weak electrolyte, the variation will be like this. This is for a weak electrolyte, We, weak electrolyte. So this can be shown like this. Okay, but for a strong electrolyte will be like this. This is for a strong electrolyte and this variation for a weak electrolyte. Ready? Okay, so let me write some points from the graph. It is clear that as concentration increases, lambda m decreases. So the relation of concentration and lambda m is inverse for both strong and weak electrolyte. Whatever be the nature of electrolyte. I think you are familiar with the term strong electrolyte, weak electrolyte. Strong electrolyte means which completely ionized in solution, right? Yeah. But whereas a weak electrolyte means it partially ionized in solution. So for strong electrolyte means completely ionized and the degree of ionization is 1 and the percentage of ionization, which means degree of ionization into 100. What do you mean by degree of ionization? Number of species ionized divided by total. For a strong electrolyte, whatever be the total, that much species will get ionized, completely ionized. So number of species ionized will be equal to total. So the ratio will be 1. So the percentage of ionization is 100. Okay. Whereas a weak electrolyte, We, weak electrolyte means the electrolyte which partially ionized. Which partially ionized means if degree of ionization is less than 1, it won't equal to 1 because number of ionized always less than the total. Okay. And the percentage of ionization will so automatically less than 100%. Fine. This is a difference between these two. Okay. So from this graph, it is clear that whatever be the nature of electrolyte, whether it is strong or weak, as concentration increases, its molar conductivity decreases because both curves are sliding down, right? Yeah. It's not moving upward. It simply sliding down. Ready? So both graph get sliding down, which means for a strong electrolyte and weak electrolyte, as concentration increases, molar conductivity decreases. Okay. So for both electrolyte, as concentration increases, molar conductance lambda m decreases. As concentration increases, lambda m decreases. Fine. Simply you are looking to this graph, in a particular concentration, in a high concentration, molar conductance of a strong electrolyte, in a particular concentration, in a normal concentration, this is the typical concentration, where the curve of W is below the curve of your SE, which means for this concentration, the lambda m of W is this much, whereas the lambda m of SE is this much. Ready? So, for a particular concentration, always the molar conductivity of a strong electrolyte will be greater than molar conductivity of weak electrolyte. Okay? So, listen. In normal concentration means the concentration not nearly zero. Concentration nearly zero means the dilution will be the maximum. Okay? That is not the case. In a simple concentration, in a normal concentration case, molar conductivity of strong electrolyte that is greater than molar conductivity of weak electrolyte. It is clear from the graph, right? Yeah. Next, variation is smooth for strong electrolyte, right? Yeah. The graphical variation of strong electrolyte is somewhat a straight line. It is a smooth variation. But in the case of a weak electrolyte, if concentration is decreasing, its molar conductivity is slightly increasing. But in a particular concentration, if concentration decreases, it gets a shoot up, right? As we decrease the concentration or as we increase the dilution, molar conductivity slightly increased. But if it exceeds a minimum concentration or a maximum dilution, then its molar conductivity suddenly shoot up. Okay, so which means that it is not a normal variation; it is a typical variation. Whereas in the case of a strong electrolyte, it always increases in a particular slope, right? Yeah. Okay, so let me explain why this happens like this. In case of, that is a very important point. In case of strong electrolyte, always fully ionized, right? Yeah. In the case of a strong electrolyte, it is already ionized, whatever it may be. It is in a higher concentration or it is in a lower concentration. It is always ionized, 10% ionized. Then why if we decrease the dilution, the molar conductivity increased? It is due to the increasing of ionization? No. Your strong electrolyte is already ionized, right? Yeah. If the concentration decreases, its ionization get increased. Why? Why the concentration decreases? Why strong electrolyte show like that? If concentration decreases, why the ionization of strong electrolyte increases? It is not due to the increase of degree of ionization. Okay, because already the degree of ionization of strong electrolyte is full. Already the full species get ionized. Then why, as concentration decreases, molar conductivity increased? The only reason is that as concentration decreases, which means dilution increases, already we know that already the ions are all ions are free. Okay, so they get more distance, right? If concentration increases, the ions have more freedom. Interionic attraction only decreases. As interionic attraction decreases, what happens? Molar conductivity increases. Okay, so in case of strong electrolyte, always fully ionized, but as concentration decreased, lambda m increased. Why means due to decrease in interionic attraction. Because as dilution increases or concentration decreases, what happens? There we get a lot of space. So intraionic attraction decreases. So decrease in intraionic attraction. So that is the reason for the increment of conductivity for a strong electrolyte. But in case of weak electrolyte, the sudden shoot up is the sudden shoot up of lambda m with decrease in concentration, right? Yeah, there is a sudden shoot up of lambda m as we decrease the concentration. Why it is so? The sudden shoot up of lambda m with a decrease in concentration, due to increase in degree of ionization, because we know that weak electrolyte is not fully ionized. So in a high concentration, there will be a fraction of electrolyte ionized. But as we decrease the concentration or increase the dilution, according to Oswald dilution law, alpha increases, which means degree of ionization increases. So more and more species ionized. If it exceeds a particular concentration, the whole electrolyte get ionized. So which increases the conductivity into a greater extent. That's why the graph is like this. Okay. So in the case of weak electrolyte, the sudden shoot up of lambda m with the decrease in concentration is due to increase in alpha, increase in degree of ionization. And the relation is, we know that alpha equal root k by c. Okay, Oswald dilution. So that's why. Okay, so we know that in a high concentration, weak electrolyte will be partially ionized. But if we decrease the concentration to a particular extent, or if we increase the dilution to a maximum, its conductivity increases. Conductivity of electrolyte get increased or shoot up, and that is due to, if we decrease the concentration to a particular extent, the alpha get full. We obtain the maximum alpha. Means the full ions or the full electrolyte get ionized. Ready? So automatically the conductivity will be increased to a higher extent. That's why the graph is like this. Okay, is it clear? Fine. So this is the most important point. Okay, why there is a gradual increment of lambda m with respect to decrease in concentration of strong electrolyte means it is due to the decrease in intraionic attraction, because there is no degree of ionization involved there, because already fully ionized your strong electrolyte. Then, but why there is a sudden shift up of molar conductivity of weak electrolyte to the decrease in concentration means already, or in a high concentration, your weak electrolyte is partially ionized. Ready? But if we decrease the concentration to a particular extent or increase the dilution to a maximum, then according to Oswald dilution law, alpha will be increased. If alpha increased means all ions get ionized, which means its conductivity increases to a maximum extent. Okay, fine. So, graphical calculation for strong electrolyte. Let me derive an equation for strong electrolyte. Okay, and here is root C and here is lambda m, and we know that this is the curve of your strong electrolyte. If you are extrapolating this one, it may have an intercept in y-axis which is defined as lambda m0, and this is a constant. There is a slope is a constant a. There is a negative slope, right? And it is having a value of minus a. Okay, ready? It's having a value of minus a. Ready? So it is nothing but this curve is plotted to here. Ready? And your lambda m value, your graph is extrapolated to have an intercept in your y-axis, and that term is defined as lambda m0. Lambda m0, or otherwise known as lambda m infinity. Lambda m infinity. Okay, what do you mean by lambda m0? Lambda m infinity means it is nothing but it is molar conductivity. Molar conductivity at zero concentration. Right? Yeah. This is a 0 point, right? 0. So here is the concentration where concentration is 0. So if the concentration is 0, then what is the molar conductivity? That is the term lambda m0. So that is molar conductivity at 0 concentration. Then what do you mean by the sense? The concentration tend to 0 means the dilution tends to infinite, the maximum dilution, infinite dilution. So that's why it is said to be. So lambda m0 stands for this term, molar conductivity at a 0 concentration. So this is the 0 concentration point. Then what is the molar conductivity? That is that y-intercept, right? Yeah. So that's why it is known as molar conductivity at 0 concentration. Or 0 concentration means infinite dilution. Infinite dilution means it is also defined as molar conductivity at a infinite, it is not concentration, infinite dilution. Or otherwise it is known as limiting molar conductivity. Limiting molar conductivity. These all are the terms which can be used for this particular concept. Okay. And this is simply a slope. Slope B minus A. So A is a constant that depends size of ions, size of the ions of electrolyte, and viscosity of medium. Viscosity of medium. So it is a constant. A is a constant which depends on the size of ion or viscosity of medium. So it is clear that you all are familiar with the equation x, y, intercept C with a negative slope m, y equal to the straight line equation. I think you all are familiar with this one. Y equal to minus mx plus c. Like that, this can be written as lambda m. This is the y term, lambda m, which is equal to minus mx minus the slope minus a. X means something in an x-axis, root c, plus c, the intercept. The intercept is lambda m0. Okay. So this is something like minus 3 plus 5. This can be written in the form of 5 minus 3. So let me write the positive term first. So lambda m equal to lambda m0 minus a root c. Okay. Or the lambda m0 is otherwise lambda m infinity minus a root c. And this is the equation. And it can be used for a strong electrolyte. Ready? A, you know the term. Lambda m infinity or lambda m0, you know the concept. Okay. And this equation is said to be, this is an equation for a strong electrolyte. Okay. Because this is derived from a variation of strong electrolyte. And this equation is known as d by Huckel-Onsager equation. D by Huckel-Onsager equation, or in a simple pattern, Onsager equation. Okay. So lambda m equal to lambda m0 minus a root c. But we can't derive an equation for a weak electrolyte because its variation is not smooth. So we simply use Kohl-Ratius law for the calculation of a weak electrolyte. But for a strong electrolyte, we can simply find out the molar conductance at any concentration, right? This means if we know the C and A of that electrolyte and the limiting molar conductivity, then we can easily calculate any molar conductivity at any concentration for a strong electrolyte. Since its variation is smooth, it is very easy. But for a weak electrolyte, it is somewhat difficult because its variation is not smooth. So how can we find the data or terms or the concept relating to your weak electrolyte means we can use Kohl-Ratius law. What it is? Kohl-Ratius law. So let me discuss the Kohl-Ratius law and its application. Fine.